chapter 5, which is natural magnetism. This chapter is very small. Almost 50% of the topics are deleted in this year. So it was already a very small chapter. Out of that small chapter, almost 50% is deleted portion. So we will finish it in 2 lectures. Hardly it will take 2 lectures. So just see introduction, what we will study in natural magnetism. See, up to now, in magnetic effect of current, we studied the current when we study the magnetic field when current passes through a wire. We basically establish relation between current and magnetic field. But in natural magnetism, we will study the sources of magnetic field which are natural. Like we will study permanent magnets. So in this chapter, we will study permanent sources of magnetic field. Permanent sources of magnetic field. So we can divide these permanent sources into 3 categories. Permanent source, you can calculate magnetic field due to an revolving electron. In an atom. So if you have an electron which is revolving in an atom, that electron is a continuous source of magnetic field. That we will study. Then we will study permanent magnets like a bar magnet. We'll study few properties of bar magnet. Then we will study earth magnetic field. Earth itself behaves like a magnet. So we'll study the magnetic field associated to Earth, which is known as earth magnetism. So we will start this topic from the basic properties of a magnet. The first topic is basic properties of magnet. Now this is very theoretical. The first property is a magnet can attract pieces of iron. A magnet can attract pieces of iron, cobalt, nickel. The first property. The second property is known as directive property. Have you ever used compass needle to decide the direction of North Pole and South Pole or East or West? Okay. We even use compass needle to decide the direction of Qibla. So no one have used, not Fatima, Johanna. So you have used. Yeah, we can use compass needle just to know the direction of Qibla. So the compass needle basically is a magnet. It works on this directive property. The directive property is if you take a magnet, a freely suspended magnet means I take a magnet, a freely suspended magnet. I can rotate this magnet and then release. Whenever this freely suspended magnet comes to rest, its north pole is always towards the north pole of Earth and its south pole is always towards the south pole of Earth. This is directive property that a freely suspended magnet freely suspended magnet freely suspended magnet always align itself in north south direction. So if you have a freely suspended magnet, then that freely suspended magnet will always align itself in north south direction. That's the directive property. Then there's third property, like poles attract and unlike repel each other. Sorry, like pole repel and unlike attract. Means if you have a north pole and a north pole, then this north pole will repel this north pole. If you have north pole and a south pole, then they will attract each other. The next property is magnetic poles always exist in pairs. Magnetic poles always exist in pairs. Means if you have a north pole and a south pole, if I break this magnet, then again this is north, this is south, this is north, this is south. You can break this magnet in any way. You will always have north pole and south pole. The fifth property is magnetic induction. Magnetic induction simply means a magnet induces magnetism in a magnetic substance placed near it. This is known as magnetic induction. It's a very general phenomena. Like if you place an iron needle in contact with a magnet, or if you keep on rubbing an iron needle with a magnet, and after a certain time, that needle becomes magnetic. That needle behaves like a magnet. That is known as magnetic induction. So these are few properties. The next are the properties of bar magnet. Bar magnet is a type of permanent magnet, nothing else. Bar magnet is a permanent magnet, a type of permanent magnet. Bar magnet have both north pole as well as south pole. So it's a permanent magnet. The next is magnetic field. You know what is magnetic field. Space around the magnet is known as magnetic field. We'll do few more properties of bar magnet. Okay, just note it down. Then we'll start magnetostatics. See, the next topic is magnetostatics basically. See, just like electrostatics, you can make a topic known as magnetostatics. Each and every term that you study in electrostatics, you can write analog of those terms in magnetism. So Earlier we did electrostat. Now we will do magnetostat. The terms that we will use in magnetostatics are just analog of electrostat. Like in electrostat, you had charge. In magnetostat, we will use magnetic charge. In electrostat, you have electric dipole. In magnetostat, we will have magnetic dipole. So no derivation is required up to potential energy. So we'll write direct analog from electrostat to magnetostat. So the first theme in electrostat is charge. So instead of charge, in magnetostat, we use magnetic charge. That is known as magnetic pole strength. We represent magnetic pole strength by small m. Its SI unit is ampere meter. Its magnetic pole strength, the SI unit of magnetic pole strength is ampere meter. So if you have a magnet, this is north pole of the magnet, this is south pole of the magnet. The magnetic pole strength of the north pole is small m. The magnetic pole strength of the south pole is small m. So that's magnetic pole strength, small m and small m. It's analog of electric charge basically. After electric charge, the next term that we had was Coulomb's law. That we wrote 1 over 4 pi epsilon naught Q1 Q2 by R square. The analog of this that we write in magnetostatics is Coulomb's law in magnetism. Coulomb's law in magnetism. I'm just writing the left hand side because using left hand side you can directly write this magnetostatics. It will help you in remember this thing. Coulomb's law in magnetism. So Coulomb's law in magnetism means if you have a north pole M1, say if you have a north pole here, its strength is M1. You have a south pole here, its strength is M2. The separation between M1 and M2 is R. So the force between them is mu naught by 4 pi. Instead of 1 over 4 pi epsilon naught, I am using mu naught by 4 pi. Instead of charge, I am using pole strength divided by R square. So in this way, one by one, we will have analog of all quantities of electrostatic. After this, the third term is electric dipole moment. Electric dipole moment is charge multiplied by separation. Instead of electric dipole moment, we have magnetic dipole moment here. Magnetic dipole moment. So if you have a bar magnet, it's a bar magnet. This is north pole. This is south pole. Its strength is M. Its strength is M. The separation between both the poles is L. So we represent magnetic dipole moment with capital M. This is magnetic pole strength multiplied by the length of dipole. Its SI unit is ampere meter square. It's a vector quantity. Its direction is from south to north. Basically, the behavior of south pole is like negative charge, and the behavior of north pole is like positive charge. If you remember, then direction of electric dipole moment is from negative charge to positive charge. Corresponding to electric dipole moment, the direction of magnetic dipole moment is from south to north. So SI unit is ampere meter square. Direction is south to north. After magnetic dipole moment, the next was electric field due to dipole or electric field on axial line. electric field on axial line. Then we had electric field on equatorial line. On axial line, the expression of electric field was 1 over 4 pi epsilon naught. It's 2p over r cube. This is the electric field on the axial line of dipole. This was third, na? This is fourth. Magnetic field on axial line. Magnetic field on axial line. This is bar magnet. This is north pole. This is south pole. The separation between north pole and south pole is here. This is the center of the dipole. This is the direction of magnetic moment. I'm taking a point on the axis of the dipole. The separation of this point from the center of dipole is r. So if you write analog of this term, then magnetic field on axial line is B. Instead of 1 over 4 pi epsilon naught, you will use mu naught by 4 pi. Instead of 2p, you will use 2m over r cube. So this is the expression of magnetic field on the axial line of dipole, mu naught by 4 pi, 2m by r cube. And its direction is same as that of dipole moment. Dipole moment is from south to north, the magnetic field is from south to north. This is in the left hand side direction. Fifth property, electric field on equatorial line. Electric field on equatorial line. So on equatorial line, the expression of electric field was minus P by 4 pi epsilon naught r cube. If I write its analog, magnetic field on equatorial line of bar magnet. Magnetic field on equatorial line of bar magnet. So this is a bar magnet. So this is the north pole, this is the south pole, and this is the equatorial line at a separation r. This is equatorial line. So the expression of magnetic field on the equatorial line is minus m by 4 pi epsilon naught r cube. This is the direction of magnetic moment. The direction of field is opposite. The direction of field is opposite to that of dipole. It's to the right hand side. It's opposite to that of dipole. Sixth thing, torque on electric dipole. The torque on electric dipole was this tau is P cross E. Just like electric dipole, we can also calculate torque on magnetic dipole or torque on bar magnet. Torque on bar magnet. So the torque on bar magnet is M cross B. If you remember, we have derived this result for a current carrying coil because a current carrying coil itself behaves like a bar, is a magnet. So just like a current carrying coil, the net force on the dipole is zero. So that's the expression of torque on a bar magnet in magnetic field. The next is the potential energy of bar magnet in uniform magnetic field. This derivation is given in NCRT, so we should at least do this derivation. So this is your uniform magnetic field. We have done a similar derivation in electrostat. Potential energy of electric dipole in uniform magnetic field. Exactly the same calculation. So this is uniform magnetic field. In this uniform magnetic field, I placed a bar magnet. This is the north pole. This is the south pole of the magnet. And this is the direction of magnetic movement. The angle between the magnetic moment and the magnetic field is theta. This is the angle between the magnetic moment and the magnetic field. So if I place this bar magnet in the magnetic field, then magnetic field will exert torque on bar magnet, and that torque is m cross b. I can even write that torque as mb sine theta. That's first equation. This is the torque acting on the dipole. I want to rotate this dipole from some angle theta 1 to theta 2 in anti-clockwise direction. Like I want to rotate this dipole from this angle when magnetic moment is at an angle theta 1 with the field to here when magnetic moment is at an angle theta 2 with the field. So we want to rotate this dipole in anti-clockwise sense. So external torque needed to be applied to rotate dipole from theta 1 to theta 2. So the external torque that you will apply will be exactly equal to the torque applied by magnetic field, because magnetic field is trying to rotate this dipole in the clockwise sense. You are rotating this in the anti-clockwise sense. So you're applying exactly equal torque that of magnetic field, but in opposite sense. So if it is clockwise, the torque due to magnetic field, so you're applying torque in the anti-clockwise sense. Can you recall this derivation that you did in potential, electric potential? The repetition, exact repetition of everything. Instead of M, we have used E there, P there. Instead of B, we have used electric field. This is it. Now I need torque. I need work done to rotate dipole from theta 1 to theta 2. So the work done in rotating this dipole from theta 1 to theta 2 is tau external dot d theta limit theta 1 to theta 2. So work done by the external torque is, it's theta 1 to theta 2 tau external d theta cos 0. I'm using cos 0 because displacement is anti-clockwise as well as external torque is anti-clockwise. Both are in same direction. So you can write that work done by external torque is theta 1 to theta 2 tau external d theta. Let's call this as equation number 3. So if I substitute those equations, then your work done is from theta 1 to theta 2. You have mb sine theta d theta. You can take this mb outside. The integral of sine theta is minus cos theta. Limit is from theta 1 to theta 2. So your work done is minus mb. It's cos theta 2 minus cos theta 1. This is the work done by external torque in rotating dipole from theta1 to theta2. This is work done by external torque. And this work done is equal to change in potential energy. This work done by external torque, this is work done by external torque, right? External torque is change in potential energy. So you can write that change in potential energy is work done by external torque, which is minus of mb cos theta 2 minus cos theta 1. So that is potential energy difference. This is potential energy difference. So after potential energy, we can even calculate this thing, potential energy only. So for potential energy, this is difference in potential energy. For potential energy, say delta U is U2 minus U1, which is minus of MB cos of theta 2 minus cos of theta 1. See, U1 comes from cos theta 1, U2 comes from cos theta 2. If I substitute theta 1 equal to 90 degree, then U1 comes out to be 0 because cos 90 is 0. I can take theta equal to theta, so I can write U2 as U. If I substitute these values here, instead of U2 I'm writing U, instead of U1 I'm writing 0, it's minus of MB, instead of theta 2 I'm writing theta, it's cos theta minus cos 90, cos 90 is 0. So potential energy is minus MB cos. So this is a potential energy minus MB cos theta.